everybody, welcome back. In today's lesson, we're going to discuss the dual nature or the wave-particle duality of electromagnetic waves. Now, more specifically, we're going to talk about the wave and the particle nature. We're going to discuss what photons are. We're going to discuss quantization and the process of quantization, and then how to calculate the energy of photons. Now let's look at the dual nature of electromagnetic radiation. Dual nature is also one of the properties of electromagnetic radiation, but what does it actually mean? It means that electromagnetic radiation can be described according to their wave nature or their particle nature. That's why dual nature is also called the wave-particle duality. But what does it mean that we can explain electromagnetic radiation via its wave nature? It means that they can undergo refraction, interference, reflection, or diffraction. Refraction simply means the radiation are moving from one type of medium to a different type of medium. Then we obviously know that the speed is going to change, and then it looks like if the wave is going to bend. Interference means waves that the waves can overlap, meaning they can be at the same place at the same time, and then they can destruct or construct one another. They can undergo reflection. Reflection means when the wave strikes a wall or an object, it can bounce back and then it can travel all the distance back, so they can be reflected or bounce off objects. And then they can undergo diffraction. Diffraction simply means the wave is going to squeeze itself through a small gap, and once it squeezed itself through a small gap and it went through the gap, and then at the other side it's going to spread out again and then move forward. But then when we are looking at the particle nature, we are simply looking at the particles in this wave. So then we are talking about photons. Photons are quantum. But what is a photon? A photon is a packet of energy found in light. So as you can see here in this illustration on the right, here we have our torch generating our light. And in this light, we can see there is small round circles. Each of them represents a photon. Photon meaning a packet of energy. So each circle contains energy. And then without these circles, there will not be any light, because light is created by energy, and this energy is carried by photons, a small packet of energy found in light. Now, what is the photoelectric effect? Photoelectric effect tells us it's when light falls onto a substance. So you can see here in the illustration at the bottom, when light falls onto a substance and the light is absorbed, it transfers its energy to the substance in fixed quantities, and then what's going to happen? It causes electrons to be ejected from the substance. So in simple terms, photoelectric effect means when light falls onto a substance, we know light carries packet of energies, meaning photons. So these photons is going to be carried over to the substance or absorbed, and then these electrons now gains enough energy, and therefore they are ejected from the substance, and now we call them photoelectrons. Now let's explain what is quantization. So quantization is still part of explaining the particle nature of electromagnetic radiation. The definition says quantization is when you divide physical quantities like energy into smaller and smaller parts, then you will reach a point where it cannot be divided any further. For example, you can only be left with one photon, so you do not get half a photon. So the smallest packet of energy that you can be left with is one photon. You cannot divide one photon even further. If you try to divide one photon, if that one photon is gone, it means the light is entirely gone. There's no light shining. So photons are then the smallest indivisible packet of energy that electromagnetic radiation is composed of. Now, how I want you to understand quantization is compare quantization to the process of tearing a piece of paper. So here you can see we have our A4 paper. We're going to start tearing this paper, meaning dividing this paper. So we're going to basically quantize this paper. So we tear the paper, making it smaller, then we end up with halves, then we're going to tear it even smaller, and then we get it even smaller and smaller and smaller until you reach a point where the paper is now indivisible. I cannot divide these pieces of paper even further. And that is then what we call photons. If you cannot divide the energy further, if you cannot divide or break down this paper even further, you have reached the photon, because the photon you cannot divide further. And then it's the smallest indivisible packet of energy. So how does this then relate to energy? So let's once again use the example of dimming lights. So if you are going to shine the light at its brightest, it means a lot of energy is going to be ejected. There's a lot of photons present. But as you start dimming the light, it means you are taking away photons. So as I'm dimming and dimming and dimming the light, I'm taking away more photons, more photons, more photons, up until a point where I have basically reached the dimmest light. If I am going to try and dim the light even more, then there's going to be no light. So then that lowest brightness that I have reached is the smallest indivisible packet of energy that I've reached, and then I'm basically left with one photon. If that one photon is gone, then the light is going to be completely gone. So that is what quantization means. It means to reduce or break down the energy up until you have reached just one photon. After that one photon, your light is going to be completely gone. But then they can ask you to calculate the energy of a photon. So remember once again what a photon is. A photon is the smallest packet of energy that is indivisible. So as you can see here in the torch is shining its light. Now this light is made up of many photons, meaning round circles, and these round circles carries the energy. And then we know that we can divide these energies, make it smaller and smaller and smaller up until the light is not shining anymore, and then the photons are gone. So we know that this photon contains energy. So I want you to look at this illustration here. So I want you to see this circle as one photon. Now this one photon is filled with energy. So the yellow color here, I want you to see this as the energy. So then they can ask you to calculate this energy of a photon. Now, what is the formula we're going to use the moment you read calculate energy? You use capital E, which is the energy of the photon, always measured in joule, is equal to H, which is Planck's constant, which is a constant once again, always 6,63 times 10 to the power of negative 34 joules per second, and then times by the frequency, which is measured in hertz. So once again, if you read calculate the energy of a photon, this is the only formula you can use. Just remember, if they give you the energy, let's say of 3 or 4 or 5 photons, and they ask you to calculate the energy of one photon, remember, then you take the total energy of the 5 photons and then you divide by 5, and then you'll get the energy of one photon. So this formula is simply used to calculate the energy of a photon. And then we can also use a combined energy formula. So if they do not give you the frequency, but they talk in terms of the wavelength, but you still have to calculate the energy, or they give you the energy you have to simply calculate the wavelength. This is the formula that you're going to use because you have enough information, because H is a constant, 6,63 times 10 to the power of negative 34. C is also a constant value of 3 times 10 to the power of 8. So this is a combined formula if you need to calculate wavelength or use the wavelength instead of the frequency to calculate the energy. This is the other formula that you can use.